Okay, so here we go. We're going to do some problems that involve capacitors. So this is about how capacitors get used in circuits. And so the big things we need to remember. Number one is that capacitance can be done as epsilon naught A over D, where A is area, D is distance between plates, and if we use a dielectric that is different than air, or a vacuum, it will have kappa. K is called the dielectric constant. It's the insulator strength. Okay, so that's the first definition of capacitance. The one that we use when we're doing calculations, if we want to just know how big a capacitor is or how a capacitor behaves, we're using those top two. In circuits, it is typically much more useful to use the fact that capacitance is charge over voltage. So this is charge size, or number of charges, over the voltage or potential difference in a circuit. And sometimes we write it as delta V equals C over, or Q over C. So let me stop and take a second to talk about that one. Remember that voltage is how much energy a charge holds. So capacitance is a measure of how much energy you can store. Capacitance is a measure of stored energy, stored electrical energy. So the reason it depends so much on voltage is because voltage, if you think about voltage, voltage is energy per charge. So if our capacitance, let's say our capacitance was 25 farads, then if we have a voltage, if our voltage is 5 volts, we can only have 5 charges, because 5 volts with 5 charges would be 25 total. It would be an energy storage of 25. If we had a voltage of, say, 2.5 volts, then we could hold 10 charges. So the idea here is that the capacitance is dependent on the voltage, because each charge that we gets some amount of energy. Voltage tells us the energy per charge. So if you have a big capacitance, you can have lots of charges that have only a small amount of energy, or you can have a few charges that each have a lot of energy. So keep that in mind as we start working some of these problems. The other things that you need to remember about capacitors, number one, in terms of in circuits, so we're on the in circuits part, when adding capacitors in series, they add as reciprocals. When we have them in parallel, they add directly. A capacitor, hang on just a second, a capacitor, when full, and remember that we use the idea of full lightly, it's about 63% full, when full, has the same voltage as the battery, and it will allow no current on its path. Empty capacitors initially act as plain wires. But as they fill, they're going to have less and less current, and then they'll have more and more charge. They'll fill up, but as they get fuller and fuller, they allow less and less current to flow through. Fewer charges can come in because they're starting to fill up. So all those things together, we're going to put together, and we're going to work on capacitance here. So I'm going to do several questions because this is new information, and so I need to do several examples. So if you look on the right with number 6, and as I've said before, if you want to watch the video, that's great, but you might want to stop every time I start to work a problem and see if you can do it before I work it and explain it. And then you can see which pieces you don't understand and ask about during review sessions. So if we start here, we've got C1 and we've got C2. These two are in parallel because they each have a branch. I can go through the top one and on through the circuit. We're only seeing part of the circuit, or I can go through the bottom one and back out. And so these are in parallel. So we are told that a voltage is applied to each pair. What is the ratio of charge stored on C1 to charge stored on C2 when C1 equals 1.5 C2? So capacitance number 1 is 3/2 the capacitance of 2. So the question is, how much charge can we hold? Well, if they both get the same voltage, let's go back and look at what our formula is here. Capacitance equals Q over V. So here's 1 and here's 2. They both got the same voltage. So that means if this one is 3/2 bigger than C2, then the capacitance on C1 is going to be 3/2 the amount of charge. Charge is in the numerator, so if the capacitor is bigger, it holds more charges at the same voltage. So number 6 would be letter C. Number 7. What happens here? A battery that can be used to complete any circuit is available. So we have a battery. It says, into which circuit should the battery be connected to obtain the greatest steady power dissipation? Okay, so we want steady, oh my gosh, I can't write tonight. That's what happens when you get tired. We want steady power usage, is what this question asks us. So in A, all of them have the same current, but power depends on current times voltage. So for all of these circuits, we're going to have the same voltage. We're going to have the same battery. So the question becomes, which one of these would give us the most current? Because most steady current will equal most steady power, since the voltage is the same for everybody. So in this case, when we do things, capacitors store energy. So capacitors are going to slow down your circuit and cause it to stop functioning. In B, A is going to have a problem because A has the most resistance, because you add the two resistors directly, so you have twice the resistance in A and twice the resistance you have in C. And once the capacitors fill up, B and C won't work at all. You won't get any power at all. So all of those are bad, which leaves us with D. So our answer is D, because you have the most energy usage when devices are in parallel. In other words, when you're running 5 devices at the same time, all on their own circuit, you're using 5 times the energy. And so parallel circuits make sense that they would be the most energy, because they're going to use, each circuit is like its own separate piece. And so the battery gets dissipated really rapidly, because it's like you're having to run, in D, you're having to power 2 separate circuits, where in A, you're powering one circuit that has the smallest current possible. So that's the trick there. Power dissipation, we want things in parallel. Okay, back to our capacitors. Let's find us a capacitor problem. Let's do number 26. It says when two identical parallel plate capacitors are connected in series, which of the following is true for the equivalent capacitance? So that means your total, they will write it like this, EQ. I can't write. Capacitance equivalent is the same thing as asking capacitance total, or the way it behaves. So if they're added in series, we're going to do 1 over C1 plus 1 over C1 because they told us they were the same size. And so the total capacitance, or the equivalent capacitance, would be 1 over CEQ. So we get 2 over C1 equals 1 over CEQ. So in this case, the total capacitance acts like 1/2 of the original. So since there are two in series, we are got them equal to each other, which means when you add them together, you get 2 on top. So when you flip them over, or when you cross multiply, you end up with half the original capacitance. So if you had a 10 farad connected in series to a 10 farad, you would actually act like a 5 farad capacitor. Okay. Now, let's look at number 29, 30, and 31, because all of these involve a circuit that has a capacitor in it. So they tell us in this one, let me get a new page, they tell us that in number 29, we want to draw a graph of what's happening with the capacitance. So when we first turn the circuit on, and this is just your teaching ideas here, first turn on the circuit, turn on that switch. What it acts like is a battery connected by a wire to a resistor back to the battery. That's how it acts. It's like the capacitor isn't even there. So you start with maximum current, and then as time passes, now we've got a situation where we've got some charge starting to build up on each plate. So now we've got some positive charges here, and this one the positive charges have run off, so it's become negative. And so now we have a back, we call that a back voltage, or back EMF. That's what they'll call it sometimes. And so you have the voltage from here and the voltage from here start to push against each other, which means your current slows down. And the longer you let it go, the phrase that AP likes to use, a long time later or sometime later, and what they mean is capacitor is charged, capacitor is charged, then here's what we get. Full here, and we get no current. Because the capacitor is doing a Gandalf, you cannot pass. You shall not pass. No current can come out because the voltage here and the voltage here are equal to each other. So voltage on the battery is the same as the voltage on the capacitor. So let's talk about now what the questions ask. On number 29, they ask, which graph best represents voltage versus time across the resistor? Well, when you first start out, all the voltage has to be dropped at the capacitor. So if this is voltage and this is time, you start up here with dropping all the voltage. It acts like just this one circuit. All the energy has to be dropped there. And as the capacitor starts to fill up, the voltage gets less and less and less for the resistor until at some point nothing flows. It stops flowing altogether. So the graph that looks like that is A. Number 30. Which graph best illustrates the current versus time? Well, you can probably guess. It's the exact same graph. Start with a high current, flatten out to a no current. So this one is also A. Because the capacitor slows the flow as it starts to fill up. It can only hold so much. And so as it starts to flow out and fill up, it's going to resist any more current coming in. Now, the question on 31 is different. It asks for the voltage on the capacitor with time. Well, the capacitor was empty to start with, so it had no voltage, and then it's going to go up to the voltage of the battery, so it's going to increase and kind of flatten out till it's getting really close to the voltage of the battery. That graph would be graph B. And then last but not least, let's look at this cute little diagram on number 33, and then we're going to go some free response questions. Number 33 says you have a circuit of 6 2 microfarad capacitors. What potential difference must be applied to X and Y so that the charge on each plate will have a magnitude of 6 microcoulombs? Okay, there's a lot going on right there. But these are connected in parallel. So the glorious thing about parallel is that when you add capacitors in parallel, and that word should be add capacitors in parallel, you literally are going to add directly. But first, we have them in series. So I'm going to look at X to Y. Here's X. And here's Y. And this is 2 microfarads, and this is 2 microfarads. So for this branch, this particular branch, and each branch is going to be the same, each branch has a capacitance of, total capacitance is 1 over 2 microfarads plus 1 over 2 microfarads equals 2 over 2 microfarads. So we have C total equals 1 over 1 microfarad. So we cross multiply here. We get 1 times 10 to the negative 6th equals C total. So that's the capacitance on each branch. Now then, what is the total capacitance for the whole thing? Well, now we're going to add all of them together. So each branch is 1 times 10 to the negative 6th. And I have 3 branches. So 3 times 10 to the negative 6th farads will be our total capacitance. Okay? That's our total capacitance. Now we had to do all of that to figure out this last piece. Because what they asked me was what is the voltage. So capacitance equals charge over voltage. So what voltage do I need to have so that my capacitance, I want each capacitor to have 6 microcoulombs of charge. So 6 times 10 to the negative 6th. And I've got delta V over here. And I want to know what amount of capacitance do I need here to figure this out. Well, I know that my capacitors are 3 times 10 to the negative 6th. So the voltage I need to have total needs to be 6 divided by 3, which is 2 volts. That's what you think is going to happen. That's what you'd like to happen. Here's the problem. And let me back up. Let's talk a little bit more about how these capacitors work. So we've got voltage coming in. So I've got positives coming in like this, and they pile up. And then negatives get left on this one because then the positives come down to the next plate, and they pile up. So if I look from X to Y, I'm not actually considering the whole circuit per se. Each one of my branches is what I need to consider. So all this would need to be considered if I'm working a problem and I have to do each one of these following each other. So then the question becomes, okay, Miss Wilson, we want the system that we see there to be the same in each place, and we want the number of charges to end up to be 6 microcoulombs. Okay, so let's go back. Here we go. Capacitance was 3 for each one of these little sections. So we had all these little sections. We got one on top, we got one on bottom. Here's the capacitors down here. So if I have each branch acts like 6 total. So do I use this guy or this guy is what we're really talking about. And it depends on how this thing is set up. What we're trying to do is we're going to have a voltage, and the voltage on all 3 paths is going to be the same. So whatever voltage we have come up here is going to be the same as the voltage that comes here, is going to be the same as the voltage that comes here. So what does the voltage see? What does it really mean to be in parallel? Well, what it really means in parallel is that we just have to do each branch as if it was all by itself. And let me come back to that. So here's what we've got. I have some amount of voltage coming in at X. Okay? When I get through these 2 pieces and I get over here to Y, I want this to be 0. So I want the voltage to be something, which I don't know. At the end I want it to be 0, and I want each plate to have 6. So here's another new use of our loop rule. And the loop rule will probably be the easier way for you to think about it. So the first thing I do, after lots of thinking, is the first step I do is I figure out this part. Each branch has 1 times 10 to the negative 6 capacitance. That's its capacitance. So I start over here with voltage. I gain voltage, and then I lose Q over C, and then I lose Q over C. This is my voltage on each capacitor, okay? And that's going to add up to 0. So V is going to equal 2Q over C. I'm going to move these 2 to the other side so we got them positive. We now know that the charge, we want the charge to be, what did they say? 6 microcoulombs. 6 times 10 to the negative third. And we know the capacitance on each. The capacitance on each is going to be, on that branch, is going to be 1 times 10 to the 6th. But each capacitor individually is 2 times 10 to the negative 6th. Whoops. I said negative 6th, then I wrote negative third. So we get on top 12 times 10 to the negative 6th. On bottom we get 2 times 10 to the negative 6th. And so our total here would be 6 volts. 6 volts is what we need, and each one of these capacitors will be dealing with 3 of the volts. So that when you pass each one individually, you use up 6 volts total, and those 6 volts total is what we're looking for from X to Y. Okay, I'm going to pause there for just a second. Hang on, I've got a phone call that I've got to deal with, so hang on for me for just a second. Let me find my pause button. Sorry about that little break for just a second. Can't always know when your parents are going to call you. So, alright, so here we go. Let's do, and I'm going to leave some of these, of course, for you to practice so that you'll have some to practice with. But let's go on down and do a couple of free responses, and we will then call it a day on capacitance. There's lots of problems, as you can see in the book. We have lots and lots and lots of problems that we can work with. So I'm going to work, there's a good one. Okay, let's look at this 2000 question from the B test, the 2000 test. We're going to look at that top circuit. I think, yeah, this is the question I want to look at. So let me get over here to my Word document, give myself a new space to work. Okay, so 3 identical resistors, okay, and a capacitor are connected to a 30-volt battery with negligible internal resistance. In other words, the battery is an ideal battery. It doesn't lose any energy while it's doing the chemical process. And switches 1 and 2 are initially closed. But 3 is open. A voltmeter is connected as shown. Determine the reader on the voltmeter. Okay, so since this is a little bit of everything in circuits, this will be a good problem for us to work. First of all, I know that the 2 resistors that are in parallel, I have to start with the resistors in parallel. And they told us that the resistance and capacitance, they did tell us the capacitance, they did not tell us the resistance. So we have 1 over R plus 1 over R equals 2 over R. So our resistance parallel piece is 1/2 big R. Okay, that's our first part. And then to get the resistance total, or the resistance equivalent, you'll see both notations used. I would add R to the parallel piece, so R plus 1/2 R is 3/2 R. Okay, so that allows us to do this. That's our first bit. Determine the reading on the voltmeter. Okay, so what is the voltage equals current times resistance? And so the voltage is going to be 30 at the battery. So this is going to be, we're going to start at the battery. And the current, I don't know, but the resistance at the battery is 3/2 R. Okay, so now divide both sides by 3/2 R. So I'm going to multiply by 2/3 R, 2R over 3, times 30 equals the current. So the 3 and the 3 cancel, leave me 10. So I get 20 over R is my current. I know this is weird because it's got symbols. We don't have numbers. But that's going to be okay. We're going to figure this out. So this is what's happening at the battery. So when I think about my circuit, just to kind of give you an idea what's happening, the only pieces of the circuit that we know right now are, I know that this is 30, and I now know that the current that comes out of here is 20 over R. When it gets to this point, since these 2 resistors are the same, it's going to divide the current. So I'm going to have 10 over R goes this way, and 10 over R goes this way. And then when they come back together, they will make another 20 over R coming back into the battery. So that's how my current is behaving. So how do I answer part A? Well, now I'm ready to answer part A. The reading on the voltmeter, whoops, don't use that marker. The reading on the voltmeter at the first resistor is going to be the current at the first resistor times the resistance of the first resistor. So we get V equals 20 over R times R. So my voltage is 20 volts. And now I know everything else I need to know about my circuit. This guy uses 20 volts. This guy, these 2 guys then will split, and we'll get 10 volts used here and 10 volts used here, so that when I take a loop all the way around, I've used up all my voltage. 20 at the first one, 10 at the second one, back around to the top. Okay, so that's the reading on the voltmeter. Now, for part B. Now we're going to switch. Switches 1 and 2 are now opened, and switch 3 is closed. Okay, so now what is our circuit in part B? It's battery and capacitor. These are the only two pieces we now have. And it's going to ask me, determine the charge, find Q, after a long time. Okay, the after a long time tells me capacitor is full. So, what does that mean? Well, if I throw out 30 volts comes out of the battery, this guy will now be charged to 30 volts. And the circuit will have stopped because they both have the same voltage and they're head-butting. The positive on this side is connected to the positive on that side, so it's like having two batteries head-on. So the capacitor is full, so now I'm going to use capacitance is charge over voltage. I know my capacitance is 1 times 10 to the negative 9th. I don't know my charge, but I do know my voltage is 30 volts. So this is a really simple one. 30 times 10 to the negative 9th is our number of coulombs. It's our charge. Sorry, that first letter should be a C. It's a really sloppy one. So there's our first one there. Okay, so that's letter B. Now, after the capacitor is fully charged, switches 1 and 2 remain open, switch 3 is still closed, and the plates are held fixed. And now we're going to put a copper block. Now let's think to ourselves, copper? Copper's a conductor. They say that right here. Why would we put a conductor midway between the plates? Okay, so now here's what I'm going to do. I need to draw this picture for you. So here's capacitor plate number 1. Here's capacitor plate number 2. This one is positive. This one is now negative. So it acts just like a battery. It faces like this. So here's our faces like a battery like this. Okay? But we now put in there copper. I'll use red for copper. And so what we've really done is we've really made this into a capacitor. So here's top and copper, and another capacitor that is copper and bottom. So it's just like we split the capacitor into two smaller capacitor pieces. And they ask me, what is the voltage between the plates? What is the voltage between the plates? So what in the world has just happened to my whole system of working? Well, it's like I divided this into two pieces, and now I have two capacitors in series. Capacitors in series add as resistors. So our capacitance now is going to be 1 over 1 times 10 to the negative 9th plus 1 over 1 times 10 to the negative 9th. So that gives me 2, 1 times 10 to the negative 9th. And when I flip that over, I get 1 times 10 to the negative 9th divided by 2, which ends up being 5 times 10 to the negative 10th farads. So now we have created a situation where it's acting like two smaller capacitors. Okay? So how do we find our voltage? Well, we do what we just did a minute ago. What is the capacitance? Is charge over voltage. Well, when you put this copper in here, guess what's going to happen? The copper, being a conductor, is going to have its positives run down to this side, and it's going to have its negatives run to the top side. So now the plate separation here is what we're concerned with. So let me put in a new page so that we can keep talking about this drawing. So now I'm going to use, for C part I, capacitance is epsilon naught A over D. Epsilon naught is 8.85. times 10, oh my goodness, 8.85 times 10 to the negative 12th. Our plate area, did they tell us our plate area? They did not. So we don't know the area. But we do know that the distance, we know the original capacitance was 1 times 10 to the negative 9th. We know the original distance was 1 millimeter. And now our distance from here to here is 0.5. The whole thing is 1, so this must be 0.25 and this must be 0.25. So how is that going to help me? Well, it's going to help me like this. I don't know the numbers in the middle. But I do know that this part on top, the plate area didn't change. The same capacitor. But what happened is I made the distance 1/4 the original distance. Which means this will now get multiplied by 4. So I have 4 times 10 to the negative 9th would be our new capacitance. And that's in farads, by the way. So that's our new capacitance. We made the distance between the plates smaller, so the capacitance went up. So now what's the voltage? Well, change in voltage equals Q over C. And this number did not change, so this was, where were we? We had 30 times 10 to the negative 9th coulombs was on top. Our new capacitance is 4 times 10 to the negative 9th farads. So our voltage is now, let's see, that would be 7.5 times 10 to the negative 5th. Whoops, I'm sorry. The 10 to the negative 9ths cancel out, yay. 7.5 volts. So you'll notice that putting a conductor in there meant that I have to have less voltage. I can't use as much energy because now I've got a conductor instead of an insulator. It's not helping me hold charge, it's helping me move charge. Okay, what is the electric field inside the copper block? CII. How are we going to do electric field inside a capacitor? Well, we're going to do just what we did a minute ago. Electric field is KQ source divided by R squared. So K is 9 times 10 to the 9th. How much charge are we holding on this plate? 30 times 10 to the negative 9th. How far is it from one plate to the other? 0.25 times 10 to the negative 3rd, it's millimeters, squared. And that would give me my electric field. I don't have a calculator on me, so I'm just going to let you guys figure that one out. That's how you set it up. How would we draw clearly the direction of the electric field between the plates? Well, drawing electric field, positive to negative, it's a uniform field. And then we do the same thing again on the bottom. So it's like we have two smaller capacitors side by side. Okay? So oh wait, hang on just a second. C3 is the picture. C4, oh wait a second. This was C4. This is in between plates. And then the one for inside the copper block would be the same thing, inside copper, but the distance would be different. It would be KQ over 0.50 millimeters squared. So this one is the one for the electric field where there's the gaps. This is the in between the plates, and then the bottom one is in the copper block. So I switched. This one is C2 and that one is C4. But it works just like a regular capacitor problem. Okay, so I'm going to stop there, and I'm going to let you, we'll probably do some more capacitor problems on review, because I know we'll probably need some help with that. But hang in there, you're doing great. We're 2 weeks from the exam. Make sure you hit some of these review sessions or get in with me in the afternoons, because starting Monday, I'll have my Zoom on so you guys can get with me anytime during the afternoon. Have a great day, and I'll talk to you tomorrow.